DARPA's Manhattan project. So this project is called Adaptive Vehicle Make, and this is DARPA's primary initiative. It's the equivalent of the Manhattan project. Basically, that's how big it is. So this is just kind of a broad overview of the entire program. AVM is Adaptive Vehicle Make. Over on the left is the development tools set. On the right, we have the MBARC was a competition between several universities where they developed an aquatic vehicle, a little RC aquatic vehicle, and competed with it using the design tools. And FANG is another design competition using the design tools. So basically the part that's of interest to us here is the stuff over on the left. So design, typically, this is the flow that you end up going through. You have your concept with your requirements, and you have your demands. You go down into a high-level design with your systems, the detailed design with the components, development installation, then you do unit testing, which verifies your detailed design. You do system verification, which verifies your high-level design. Deployment, you compare that against your demands to make sure that it meets them, and your system validation to make sure that it meets all the requirements specified in your concept. So you can't verify where you started until you get to the very end. So we want to kind of break things down. So when you start using modular components, you don't have to worry about the detailed design or unit testing because you're using the same components over and over again. You test them once and then you never have to check them again. So that's kind of where the square tubing and basically items that you've used in the past become valuable because you've already done testing on those, so you only have to verify the system after those components have been verified. The problem that's occurring at OSE is you go through this shortened design cycle because you don't have to verify those individual components, but you don't have the other half because as soon as you finish development, you send your machine off and there's not really a whole lot in the way of feedback. And there's no instrumentation machines to determine if they're actually meeting the original design requirements. I mean, you can go out and lift something, but you don't know how much it could actually lift. And you don't know if there are other problems occurring that you just don't have the way to monitor. So there's no system verification or system validation. And then you come back and start developing the next model without basically getting all you could have from the previous version.
But that's the particular case right now. We didn't have that. That's not what we want to do, and that's not what we have done.
Yeah. That's not what you have done? Sorry.
No, I mean most of the machines until recently have been here.
Yeah.
I mean, we've been using them primarily here.
But you do want to be able to deploy them, correct?
Yeah.
So, I mean, you would like feedback from the people who are actually using them.
Right.
And I guess that's kind of where this is trying to...
Yeah, we're missing... I mean, we don't have any feedback loops from people using the machines so much. I mean,
we don't even have feedback loops for ourselves really using the machines either. I mean, there's mental notes that it seems like are being made, and maybe some notes in the wiki, but there's not a formal evaluation process.
There's no hard data.
Right.
So.
And that's kind of...
I think that's your point.
Where we're good.
Yeah.
Okay,
exactly.
okay, good.
Yeah. So, one thing so this isn't part of Adaptive Vehicle Make. This is another project opportunity, or another proposal opportunity that Vanderbilt is working with currently. This is the dive board. It is an integrated system on a chip. So basically, if you have something like an Arduino, this has built-in instrumentation. So if you were to equip a machine with this out in the field, then you would be able to have it send back data of the machine actually operating, which would allow you to create models and make them more, true to the
match
reality.
the model. Yeah. You might match the model simulation.
There's just a word for that. I'm not remembering it right now.
Yeah.
But that's not the main point. But that is a potential opportunity for development that we're exploring, and this might be a good application for.
Let me go back to that for a second.
Yes.
Is this in development, or do they have this?
So it exists. They have someone who's going to manufacture these boards for them, and then they're going to continue development.
So how exactly does it work? Because we have something similar when we do flight testing.
Right.
is we have something that we actually put in one of the seats, but then we have to put like diodes on certain parts of the aircraft, so it can read the vibration, it can read the RPMs.
You have to have sensors, yeah.
Yeah. So does this require sensors as well, or is it?
Yes. I think so.
Okay.
But I'm not quite the right person
Okay.
to ask.
Fair enough.
So we're going to go into a little bit on system verification, which is where the meta tools fit in a little bit more. Yeah, that was the right slide. Okay.
Whoa.
So, you were talking about earlier your backhoe and how it failed at the pivot. Maybe a few other places, I don't know. But in any case, this is just a simulation in Creo, and you can see right here that the stresses are high, and so that's going to be where it's going to fail.
Failure rate, right.
So this is just an advantage to using just basic CAD simulation. Here is a depiction.
Is that what we have? Is that real to us? That's the current. Is that the actual current model, or?
Yep. They took the model that OSE had online and then generated it in Creo and then did a stress analysis on it.
Mm-hmm.
So yeah, that's fairly realistic.
Now, how do they generate that model?
I think that's just in Creo. So just apply loads and.
No, how do they generate the model itself? How do they transfer what
they
we
drew
had
that
to
one.
that? So they just straight up looked at it and then drew it in there? Okay.
They imported SketchUp.
They might have, but I don't.
Well, that would kind of, I guess that's what I was alluding to, is can they import files or do they have to start from scratch?
We're getting there.
Yeah. Okay.
But yes, we can import.
Awesome.
So, and over here is, we'll talk about this a little bit more in a second, but this is a diagram of the welder. Should I just skip ahead to there?
Was there a video there?
We'll get back to it.
We'll get back to it. It's not that interesting. I'll show you in a second. Okay. So this is kind of what the adaptive vehicle make wants to do. So just kind of the general premise is to get the entire development cycle in industry 5 times faster. So this is obviously not industry, but the same principles are applicable. So basically we're going to focus on up to here because over here is full-scale fabrication, and that's not quite where we're at. So first, here, in current design, we have a few dozen concepts that are generated, whereas if we have a huge part library to pull from, we can generate far more concepts without having to kind of do them all manually. Next comes the number of virtual model simulations we can do. Typically, you only do a few of them in regular design just because of the time constraints for doing one. And then a few dozen, component designs, whereas if it's all virtual, you can run through iterations much, much faster. Actual prototypes built, if the first 2 steps take a lot less time, you have more time to actually build prototypes, whereas normally they only build a few prototypes, and then they do a whole lot of testing on them. An example of that is the Joint Strike Fighter aircrafts. Each company made 2, and then they tested them a lot. So thousands of iterations of tests, whereas if you have a good computer model, you only have to do a few tests, compare them to your computer simulation, fix your simulation so that it matches the real thing, and then once they're synced up, you don't really have to do any more testing because the model is now sufficiently accurate. So to go into a little more detail on the virtual model simulations, this diagram basically is intended to show that this entire space between the axes is your design space. And if you have an automated software, you can explore the entire design space instead of just a few pieces. So, and I guess an example that might be relevant here would be you have cylinders for your machines, and you want to use the same cylinder in all the machines if possible. So if you have one machine, you can go through, you say you have 10 cylinders, you test each of them, figure out which one's the best. But let's say you've got 10 machines and 10 cylinders. Now you've got to run 100 iterations before you can figure out which one is the best for all possible configurations. So if you have a way to automate that, you just swap out that one component, run the analysis, and then it'll tell you which one is the best for all of your machines. So now, if in the future some new cylinder comes out, and you're like, oh, is this one better than what we had previously? Let's just stick it in. run the analysis through all of them are machines that are already developed, and we'll know fairly quickly. Okay, so now we're back to this is something that we can do right now. So here's the welder schematic that was developed at OSE. So basically we took this schematic and we converted it, I'm going to have to jump out of the PowerPoint real quick, to a model in, can I zoom in more? I guess you can see that okay. A model in Open Modelica, which is a simulation. So basically it gives you the same idea of what the system is, but now we can run a simulation on it. So by running that simulation, this is just a generic model because we didn't have the exact specs of the welder that they were using here. But if we had those, then this could become an indication of how the welder ought to behave given those inputs. So we'll just let that simulate. Did we run out of juice? So, Martin, you were saying that the issue that the welder was having was it was overheating, correct?
The gun was overheating.
The gun was? Is that what it was? Okay. So if we go here, our gun would have been about here. So that's the thermal resistor 1. So if we go back in here, we can open that guy up and follow its... Which one do I want? Heat port. And follow its temperature profile. So we can determine what its steady state temperature is going to be and if that's too high or not. And then we can change other components in order to bring it down. So being able to create that model and then just vary those components in order to get the operation that you want is advantageous. So this is something that can be used immediately. In order to use the iterative process, the part library has to be developed. And so that's where, I don't know if I jump back into the presentation. That's where our warehouse comes in. So my plan when I go back to Vanderbilt is to, what's the word? Basically take these components and bring them into the meta universe. And that way, by creating the constraints, you can have it auto-assemble. So for example, I think this is what I'll probably start with. I'm not sure. If it's not valuable, let me know. But if it is, then I'll do it just because I think it's simple enough that I could do it fairly quickly. Basically, optimizing the power cube so that you could change the engine and it would dynamically recreate the power cube, positioning the components, and figuring out like how big it would have to be to minimize external volume.
So like automated packing?
Yes.
Of the power cube?
Yes.
Sure.
I think it's simple enough that I could do it and show kind of the capabilities of the software in its current state.
And then if you were doing that, you could change out the components and then it would pack the new components that you put into it, right?
Yes.
And can you also change the dimensions of the power cube itself?
It would do that. That would be what would
So
automate it.
basically, like, you take a current power cube that we have right now, right, and say we want to put the Kubota engine in a power cube instead of the 27 horsepower one that we have, Briggs & Stratton, I think is what it is.
Yes.
So would it then say, okay, well now you need to extend this out 1 foot and you can shrink this foot and this is where you put everything?
Yes.
Awesome.
Yep.
I like it. So
And then if you had other constraints on the system, like, well, I need this many horsepower at the wheels, you could add that as a constraint and say, well, all those engines aren't going to work. Or if you knew how much loss you had in your oil system, you could say, okay, this should be enough. Oh, losses. Not going to be enough anymore. You could also have it determine how fast you can drive, whether or not you can operate your loader arm or drive at the same time. You'd be
So
able
it's
to
an entire
determine.
systems analysis.
Right. Like as long as the system is defined, you can analyze everything. And then just by swapping out a component, and by having that component library, you can check all the iterations to see which one will operate in the best way. So,
Wow, that's awesome.
The changes are ideal.
Right? So, product development currently is lacking two major things: simulation and testing, and then validation and verification. And that's where we're trying to kind of basically automate that and make it just a lot easier. And they allow you to explore a much greater designs. Like, they allow you to look at a lot more options just because of the physical limitations of time and resources. If you can simulate them, you can get through it a lot quicker. Probably the main holdup right now is the fact that the parts library is still in its infancy. So as we go testing more things and adding more to the parts library becomes more and more powerful and allows us to do more design combinations and iterations. So basically it's, oh, we want to test out this engine, implement that, and then we can start testing with it. So then our last bit. So we think these tools can help OSE reach its goals of scalability and quality design, and ultimately provide, as Martin likes to say, the means to save the world. So what we would like to do is, Jonathan and I, we're going to help kind of, just for the next short term, help optimize important models, starting with PowerCube and the Welder. With the PowerCube, the design space exploration, and with the Welder, the system verification to make sure that it's going to do what it is that we want it to do. And then for long-term goals, ISIS they're a research institution, so they want to write proposals. So they want to be able to write joint proposals with OSE, because they've done RC competitions, they've done the FANG competition. DARPA doesn't seem to really, they want to do cool stuff, but they don't really care where the tools are tested, they just want them tested. So if we can write joint proposals, then we can get funding to do these kinds of things and implement them with the things that are being built here. We also want to develop a relationship between the universities, Vanderbilt and Brigham Young here, and just flesh out that component module system library. Because as you decide you need more components, we can gradually add those. The library becomes more usable, more people want to use it because it's more useful, and then the whole thing can grow. And as more people are interested, they'll start adding components as well, and then you don't have to do all the work. Other people are collaborating with it as well.
So is this open sourced, or do you have to buy this?
No, this is all open source. So.
Go Mormons!
That's really, really cool.
Wow. Impressive. All right. Libraries and simulations. That would be good.
Yes.
And we need to get our end structured so we're able to have the capacity to do this.
Right.
So
Utilize it.
that's all I'm thinking. I mean, this is great. Now we need to get our shit together on our end.
So, I mean, we can start coming up with, I guess, kind of walkthroughs or documentation for how to do, at least I plan to document fairly well the PowerCube and the Welder as how to use the tools to do that, because those can be done pretty much right now. And then as things scale, it can become more closer to what it's supposed to be. But yeah, DARPA is, this is their thing right now. This is their big project. So there's somebody with lots of money who's got a vested interest in this.
That's nice.
Yeah.
Rob, what do you think?
Rob?
Can we get the camera in a little closer to the screen, zoom or closer? Wow, amazing. Great. Who's ready?
Okay. Great. Excellent. Thank you.